Good morning. This is going to be chapter 10, which is the last chapter in Chem 111. And we're going to do this in two parts. We're going to do one today, and then when we meet back, we'll do the second part. And then that will complete the lectures for this course. So we've already done the thermo chapter. It was just part of the chapter 9 that we did, that first half of that. So you should already be working on that and getting familiar with everything. And then the chapter 10, which is just about gases. There are quite a few calculations in this one, though, so you need to make sure that you're keeping up as we go through these, and take the time over the weekend or whatever to get familiar with that. So we're going to talk again about the last time you got to hear about kinetic molecular theory. We're going to look at the different laws that are associated with gases and how those apply to calculations. We're going to apply the kinetic molecular theory to those laws, compare motion of gases with liquids and solids. We're going to look at density, molar mass, and molar volume, and how to calculate those. Mole fractions, which we've already seen, but there's a little bit different slant on it. We're going to use Dalton's law for that. We're going to relate how stoichiometry applies to gases, and then we're going to recognize the components of van der Waals. We're not actually going to do van der Waals calculations. Going to understand what it's correcting for. So you may remember gases from the very beginning of this semester when we talked about the differences between gases, liquids, and solids, and we talked about the kinetic molecular theory for the first time. And basically this kinetic molecular theory talks about the motion and how these molecules and atoms move. Gases are randomly moving. They're very fast, and they're very separated from each other. They move in straight lines, and then they'll either collide with the wall of the container or another particle, and then they bounce off. And so when they do that, they don't really exchange a lot of energy with whatever they impact. They just use that change in energy to change directions. And so the molecular collisions due to this movement and ramming into each other is what produces the pressure in a container. So by definition, pressure is force per unit area. And so as they are striking the surface or other gas molecules, the more force they exhibit within a certain area gives them a higher pressure. So if I do anything to speed that up or make those stronger impacts, then I'm going to increase the pressure. And so this gas pressure, as I said, this constant movement of molecules is what's causing that as they collide with things. And it depends on how many gas particles you have, the volume of the container, so how big is it and how much room do they have, and then the average speed or velocity of those gas particles. So anything I do to increase the velocity of the particles, decrease or increase the size of the container, or increase or decrease the number of gas particles, that is going to affect the pressure that's inside this system. So if you recall, kinetic theory of gases tells us that all of these impacts are elastic. That is, they don't exchange energy with anything, they just change direction. The inelastic collision is like a head-on collision with a car, where you actually hit and you're exchanging that energy between the two. Whereas an elastic collision, you just hit and bounce off and hit and bounce off of each other. And so you're not really exchanging energy at this point, you're just changing direction of that initial. And so this is the type that we're going to see with very little or no exchange in energy between the particles and the surface. So looking at these individually, the concentration of the gas molecules, the higher the concentration, the greater the pressure. Okay, so the higher the concentration, the greater the pressure. So if I keep the volume the same and I increase the number of particles, then I'm going to increase the pressure. Low density particles results in low pressure, high density. So the more I have, the higher that pressure is going to be. As the volume increases, the concentration of the gas molecules decreases, okay? But since the volume increases, the concentration goes down. So we're going to see how if you have, as you increase the volume, okay, you're going to decrease the concentration because you're going to spread them out farther from each other. But and so that would also then decrease the pressure because you decrease the concentration. So you got fewer and in a per unit area, and so they're going to have a lower pressure. So I couldn't really talk about atmospheric pressure effects and things like that, or pressure in general, without talking about atmospheric pressure effects. This is what creates the wind, these pressure changes. And these pressure changes kind of give us a clue as to what's about to happen to the weather. And so you'll see on a weather map that you have a high front and a low front. Okay, and the pressure, and usually if you have high pressure, you have clear weather, and if you have a low pressure, it's changing. Now it just depends on what the other parameters are as to what it's changing to, but you back here you're going to be stable, okay, and so that's the nice weather. And then as this front comes through, you're pushing that instability as you go down. So that's what you're seeing when they're talking on the weather map. Also, as you increase in elevation, as in, you know, climb a mountain or whatever, as you get higher and higher, the concentration of the air gets lower and lower. And so because of that, the pressure decreases as well. So as you get higher in elevation, like if you went to Denver, you know, they call it Mile High Stadium for a reason. You're very high above sea level, and so your atmospheric pressure, or the pressure pushing down on you, and the concentration of the air and oxygen is going to be less. So how do we measure pressure units? Well, the atmosphere is the standard, okay? 1 atmosphere is the standard, and that is basically the average air pressure at sea level. Everything else is how much does that equal an atmosphere? And so when you're going from one to another, a lot of times you're going to compare it to atmosphere and then compare the other one to atmosphere. I'll show you what I mean in a minute. I also want to point out that a Pascal, if you have, sometimes you'll see 101.3 kilopascals, okay? That's the same as an atmosphere. So you can have 101,325 pascals or 101.325 kilopascals. And so that's all equal to 1 atmosphere. 14.7 psi is the same as 1 atmosphere. 760 torr, or 760 millimeters of mercury. Those are the same unit. Inches of mercury, and then bars. And so you've got a lot of different ways, depending on what science you're dealing with, to discuss atmospheric pressure or pressure in general. We in this country use mainly millimeters of mercury when we're talking about, you know, it's rising or whatever. This came actually from the way we used to measure pressure. Was we had an open container of mercury, okay, liquid mercury. This was before we knew how toxic it was. you would put a glass tube with a vacuum in it, and so it would pull it up to a certain level that would equal the outside pressure. So, and they found that this was traditionally 760 millimeters or 29.92 inches of mercury in this tube. And then if the pressure increased, it would push on this bath and cause it to rise in the tube. And so if it went above 760, then this would rise, and you could measure how many inches or how many millimeters it was at that time. And then the same way, when the pressure would release, okay, so the pressure wouldn't be as high, then what was in here would drop. And so that's how they would measure it. And they would have these things sitting out on the counter, especially in labs, and, you know, mercury coming off of it and everything lovely. But that they used mercury because if mercury's density is so high that you could do a short tube of it. If you used water, you'd have to have, like, you know, 12 feet or something high. So that's why they used mercury in the beginning, because it worked well. So the first types of problems we're going to do is just how do you convert between these different units. And you will have this table, so you'll be able to see it. Just remember, I told you about the kilopascals, that it's, you know, 101.3. I'm trusting, you know, it's 101,000 pascals at 101.3 kilopascals. Should come to you pretty naturally by now. All right, so a cyclist inflates her high-performance road bicycle tire to a total pressure of 132 psi. What is this pressure in millimeters of mercury? So the way the book suggests, and I actually suggest this as well, is that you look at, since everybody has the 1 atmosphere in common, you can convert whatever your first one is to atmosphere, and then convert the atmospheres to the second unit. So if you're given 14.7 psi, okay, oh wait, that was another one. 132, that's the unit. 132 psi, that's what's given to you in the problem. And we want to get rid of psi, so 1 atmosphere is 14.7 psi. And then you want to convert atmospheres to millimeters of mercury, because that's what you want. And so it's 760. And this 760 number you'll become very familiar with, because that's one you use quite a bit. And so when you just do the math, you're going to get 6824 millimeters of mercury. And so if you really wanted to be exact on your sig figs, you'd have 6820 millimeters of mercury. And, you know, for testing purposes, it's a good idea to go ahead and write them all down at first, and then you can change them to the sig figs. I am a little more lenient on the sig figs at this point in the semester. And you do the calculations rather than, you know, because we've already talked about the sig figs. All right. So either of those answers would be acceptable to me. So just notice I went psi to atmospheres, and then atmospheres to millimeters of mercury. And that's the easiest way to do it. And then you don't have to think too much. You just get rid of those units. And then I gave you a couple of these. And this is inches of mercury right here. So it's inches of mercury. Some people get a little confused by that, so just make sure whenever it does IN mercury, that's inches of mercury. Okay. All right, so how we measure this now is, you know, of course we use things other than mercury now, obviously, but there are two instruments that we use to measure pressure. One is a manometer and one is a barometer. Okay, a manometer gets the pressure of something that's trapped in a container. Okay, so if you have a gas trapped in this container, I can open a valve or whatever, and I can see what it does to this tube, okay? And the change in height of this tube is going to tell me what the difference is. So it has this U-shaped tube. You fill it with a liquid, you connect it to the gas here, and then you open it, all right? And then what it does is this is pushing a certain amount, and atmospheric pressure is pushing a certain amount, and so you're going to see the level here of which one is higher, okay? So the difference in those liquid levels is a measure of the difference in pressure between the cylinder or whatever you're doing and atmospheric pressure. So a manometer is measuring pressure from something that's kind of a closed system. And if you've ever had your blood pressure taken, most of you should have, they use something called a sphygmomanometer. It's a mouthful, okay? But notice, manometer. So when they pump that up, they are pumping up a bag of air that squeezes off your arm in a certain amount of pressure, and they can see that pressure. And by listening to the sound of your heartbeat underneath that pressure, and then when it goes away, they can tell the two numbers that they're going to report for your blood pressure. So that's an example of using a sphygmomanometer. We'll talk about the other type a little bit later, and that is a barometer. And barometer is a measure of pressure. So it's just what's ever in the surroundings. So basic properties of gases. So when we look at gases, we're going to be talking about these 4 items right here. And they are all proportional to each other in different ways, and they all have simple gas laws associated with them that describes these relationships. So what we do when we go through gases is I'm going to go through each of these laws, and then I'm going to combine all of those laws at the end, so that you have basically one formula to go by. You just put whatever numbers in that you're looking for. All right. So if you keep 2 of these constant, then you can use the other 2 to see what the changes are. But you'll see when we get to the end that we can actually solve for all kinds of things with this basic formula. Oops. All right, so the simple gas laws are Boyle's Law, Charles' Law, and Avogadro's Law. Okay, and you remember Avogadro, he's the mole number guy. That's how many, 6.022 times 10 to the 23rd atoms in a mole, right? Boyle's Law looks at the relationship between pressure and volume. Charles' Law looks at temperature and volume. And then Avogadro looks at the number of moles versus volume. Okay, so all of these have volume in common. All right, and so we call these the simple gas laws. So Boyle's Law says that the volume of gas is inversely proportional to the pressure. Basically what that means is if you increase the pressure, volume, you decrease the pressure, and vice versa. Okay, so whatever you do to one, you're going to do the opposite of the other, and it's going to be equal in magnitude. So if I have 1 atmosphere of pressure in this cylinder, and I double the pressure, so I had 1, now I have 2 kilograms, then I am going to half the volume. All right, so if I increase by 2 the pressure, then I decrease by 1/2 the volume. So it is an indirect proportional or inversely proportional. As pressure increases, volume decreases. As volume increases, pressure decreases, etc. The only reason I really show this slide is just, the book has it. It shows you that it is a proportionality thing, okay? And what it gives us is this very important relationship, and that is If I have a certain parameter set up where I have a pressure and a volume, if I change one of those, the other one is going to change so that those are constant. So P times V is constant. So this number is going to have to be equal to that number. So what that allows me to do is if I have a P and a V and I change P, then I can calculate V by just setting those two things together. One cool application of Boyles Law is scuba diving. And for anybody who doesn't know, I used to be a very avid scuba diver back in one of my other lives, and I was an instructor for a while. And so this was very near and dear to my heart. So for every 10 meters that you go underneath the surface of the water, and approximately, you're going to get for every 10 meters, you're going to get 1 additional atmosphere of pressure. So when you're at the surface, remember, you already have 1 atmosphere. So when you get 10 feet, right? So when you go down 10 feet, you're going to be at 2 atmospheres. When you get down to 20 feet, you're going to be at 3 atmospheres. Okay, and so if you've never been 20 feet or 20 meters, I should say meters. All right, sorry, big difference, right? That's 30 feet and 60 feet. When you go down 10 meters or 30 feet, you're going to feel twice as much pressure on you. Now, you might not feel a whole lot different, but if you go down 60 feet, 30 meters, then you are going to start to really feel the effects of that. And your mask that you have on is starting to squeeze to your face. Okay, but what gets important is your lungs, because remember, your lungs are like balloons, and as you breathe in and out, okay, you are expanding and then contracting those lungs. And if you don't blow out and you hold your breath as you go up, you're releasing pressure. And we already said, as pressure goes down, because I'm going towards the surface, the volume is going to increase. So if you had your lungs full of air and you held your breath while you went up, you could theoretically burst your lungs. So that's why one of the big things they teach you when you learn how to scuba dive is to always exhale when you're rising, because you've got to relieve that pressure, because you're going to feel like your lungs are getting more and more full as you go up. So the first law is Boyles Law, which is P1 V1 equals P2 V2, and that's the application for this law. And so when you do these gas problems, I strongly suggest that you take inventory every time. All right, and so because you need to keep up with which one is in the first set and which one is the second set. It doesn't matter which one you call 1 or 2, or if you want to call it initial and final or whatever, as long as you keep the right ones together. So a woman has an initial lung volume of 2.75 liters. Okay, so that's initial, so I call that V1, 2.75 liters. All right, which is filled with air at an atmospheric pressure. Okay, so it's filled at a pressure, so that's also the first condition of 1.02 atmospheres. If she increases her lung volume to 3.25 liters, okay, so I'm changing the volume to 3.25 liters, so that's the second volume, without inhaling any additional air. What is the pressure in her lungs? So what does that pressure change to? So I'm given 2.75 liters at 1.02 atmospheres, and I'm going to change the volume to 3.25 liters, and I want to know what that new pressure is going to be. And so I use my P1 V1 equals P2 V2. Now I'm going to rearrange this. You can put the numbers in if you want to first, but if you really should practice putting in the correct way to rearrange these. So if I'm solving for V2, I'm going to circle that, and I'm going to say, okay, to get rid of this, I'm going to divide both sides by P2, right? So I'm going to have P1 V1 over P2 equals, and then I've got a equals V2, right? And so once I do that, I am just going to plug those in. Now you could have you could have just done numbers and then rearranged them. Like I said, it really doesn't matter. But I'm just going to solve for V2 if I do it this way. The only thing that's critical over here in your inventory is you got to make sure that everything's in the same units. All right. Temperature, when we get to temperature, is always in Kelvin. Okay. Everything else in these laws can be whatever you want them to be as long as they are the same units, because the proportionality will remain the same. So then I have that V2, no, P2, sorry. I was looking at it wrong. So this is the same here. Whoop. So I've got P2 and I do V2. Sorry about that. So luckily V2 and P2 were the same. So I get the same exact thing. I just had those two mixed up. So P2, and you're gonna, just like what I just did, if you don't pay really close attention to it, you're gonna get these because you got so many V's and P's and all that. I need to drink more coffee. All right, so P2 equals P1, which is 2.75 times P1, which was 1.02 atmospheres, and this was liters, and then divided by 3.25 liters. And so I should end up with a pressure. So P2 is going to equal atmospheres, and then I just do the math, 0.863. Sorry, I'll pay better attention. All right, my mind is thinking ahead of me. So let me just, I'm gonna redo this down here so you can see that it was P1 V1 is equal to P2 V2, and then I was solving for P2, so I divide both sides by V2, and so those cancel, and so I got P2 equals P1 V1 over V2, and then I plugged in. If you just put it in like it was initially, okay, then you could just put your 2.75 times 1.01 atmosphere. It's kind of like a ratio and proportion. If you've seen those, 3.25 times X, basically. And then divide by 3.25. And then X equals 0.863 atmospheres. So the point is you can either go ahead and rearrange it at the beginning, or you can put the numbers in and rearrange it at the end. Whichever one is more comfortable for you. It doesn't matter. You're going to get the same answer. But being able to rearrange equations is a skill, so it's probably one that you want to know. All right, so that was Boyle's law. It's said as volume increases, pressure decreases, and vice versa. So Charles' law. Charles' law shows us the relationship between temperature and volume in gases. And the volume of a mixed amount of gas at constant pressure, notice those other two things are being held constant, increases linearly with increasing temperature in Kelvin. That means it's a direct relationship. So that means if I increase temperature, I'm going to increase volume. And don't forget, the opposite of that is true as well. If I increase volume, I'm going to also increase the temperature. That one's a little mind-boggling, but you know, gases have their own rules for a reason. Okay, and so the rule for this one is that V1 over T1 equals V2 over T2. Or you can write it the other way if you need to. And if you're solving for temperature, I suggest that you go ahead and you invert it. Because remember, you can do anything to a number you want to, as long as you do the same thing to both sides. And so if I was solving for volume, I'd write it this way. But if I was solving for temperature, I'd write it with the temperature on top. You just have to make sure that you maintain that same proportionality. All right. Now, this is directly proportional to your absolute temperature, and that's in your Kelvin scale. Okay. Any temperature you put in any of these gases needs to be in Kelvin, period. So try not to forget that, because you will be off quite a bit on your calculations as you do that. And this is because you theoretically have no movement or almost no movement at absolute zero. And so as you increase the temperature towards room temperature, you're going to increase the molecular motion, and that's going to over a greater area, okay? Because you're not able to change the pressure, but you can change the volume in this, all right? And so this is just kind of showing you what that means, that this is absolute zero, which is negative 273.15 degrees C. And then as you approach, I think we have 500 C is the max here. You're going to see that if you have 0.25 moles and 1 atmosphere of pressure, you're going to have a linear relationship between increasing volume and an increase in temperature. Okay, and that's just showing you graphically. And so a great example of this, and you can, you know, if you want to look it up on YouTube or something, I guess I should do one, but if you have a balloon and it's not like completely blown up, like, you know, it's not blown up to the max or whatever, so you got a little bit of room for expansion before it pops, and you have it at a certain volume. Okay, so let's say it's like that big. Okay, and so that's how I blew it up. And so if I put that in an ice bath, I'm going to lower the kinetic energy of those collisions, and so my volume will go down. If I put it in a hot water bath, almost boiling, then it will expand and it will get bigger. And you can do this same thing putting it in the freezer. So if you're interested and you have a balloon, you can take a balloon, blow it up, you know, not tight, where you've got, you know, some room one way or the other. Put it in the freezer, you'll see it get little. Put it in a really hot water bath on the stove, and you'll see it get bigger. And so that is Charles' law, because as you increase the temperature, you increase the volume. As you decrease the temperature, you decrease the volume. So here's an example of the how you work Charles' law. And like I said, I always write these at the beginning. So this is the original Charles' law, V1 over T1 and V2 over T2. What you need to remember about these laws is what is the relationship. Boyle's law, you have an inverse relationship that is as volume increases, pressure increases. In Boyles Law, you have a direct relationship. As you increase volume, you increase temperature and vice versa. Okay? All right. So a sample of gas, and notice all of these are changing something. So we're comparing a change. So we have two situations. So you have a sample of gas with a volume of 2.80 liters. Okay, so this is my sample, so I'm gonna just call that V1, and it's at an unknown temperature. So T1, I don't know. Okay, when you submerge it in ice water at a temperature of 0 degrees C, its volume decreases to 2.57 liters. What is this initial temperature? All right, so I know my relationship. I know that I have to have the same units, but remember on temperature, it has to be in Kelvin. And I don't care if you do 273 or 273.15, it's up to you. But I typically don't put the 0.15, but you're very welcome to if you want to. All right, so I've got it in Kelvin now, and I've got it in liters, and so I want it in Kelvin, and then I want it in degrees C. Always look and make sure you know what you're being asked for. So I want it in Kelvin and in degrees C. So I'm going to remind myself right there. All right, so there's my inventory. I have inventoried, I have translated what I need to. So now I can just plug it in. So since I'm solving for temperature, I'm going to use the version of T1 over V1 equals T2. And I want to get rid of V2 on my right hand, or no, on the left hand side, because I want to know what the original temperature was. So I'm going to have to multiply both sides by V1, and that will get rid of the V1, and then that will leave me T1 equals T2 V1 over V2. Once I get to that point, I plug and play. T2, make sure you're going to the right one, 273K times V1, okay, 2.80 liters, divided by V2, which is 2.57 liters, and that's going to give me T1 in Kelvin. And that should give me 298 Kelvin. And then since it asked me to do it in both, I'm going to have to say 298K minus 273K equals 25 degrees C. So it was at room temperature, not a big surprise. Okay, so this one again is you're just farming, data mining, if you will, the numbers out of that so that you can take an inventory, deciding which is the first condition, which is the second condition you changed it to, and then make sure that your temperature is in Kelvin and all the other units match, and then you can just plug it in. So we're just plugging into a formula. All right, and there's your practice. All right, the third law is Avogadro's law. And Avogadro's law says that volume and moles are also directly proportional. Okay, volume and moles of gas are directly proportional. So if you increase the number of, or if you increase the volume, you're going to increase the number of moles of gas. And as the amount of gas increases, the volume increases. That's really the easier way to think about it. So if you add more moles of gas, you're going to increase the volume of the gas, as long as your pressure and your temperature are constant. Okay, so you can't change those other parameters for this to be correct. All right, so when we looked at liquids and things like that, equal volumes meant equal molecules. In gases, that not work. Okay, so the volume of the gas is going to increase directly with the amount of volume. All right, so this gives us, again, a V1 over N1 equals V2 over N2 relationship, where N is the number of moles of gas, only gas. So if you have mixed things, you only look at gas when you're looking at this. All right, so the volume of a gas is directly proportional to the number of gas molecules. If you increase the number of gas molecules, more of them are going to hit the wall at the same time. All right, and so since you can't increase the pressure, you have to increase the volume. So Avogadro's law, it says that we are looking for moles in this one. So a male athlete in a kinesiology research study has a lung volume of 6.15 liters. All right, so I see a volume and I'm going to write that down, 6.15 liters. During a deep inhalation. At this volume, his lungs contain, so those two go together, 0.254 moles. During exhalation, his lung volume decreases to 2.55 liters. All right, so I have a second volume. It's 2.55 liters. How many moles of gas does the athlete exhale? Okay. I'm going to write that down because that doesn't sound like it's going to be a direct thing to me. Okay. So liters, that was 0.254 moles. Then when he exhaled, he had 2.55 liters left. And it wants to know how many moles did he exhale. Notice they're asking how many did he exhale, not how many did he have left over. So we may have to do something a little bit different at the end of this problem. But first we need to just plug our stuff in. All right, so since I'm solving for N, I can do the same thing that I did on the other direct proportional. I can say N1 over V1 equals N2 over V2, right? And I'm going to be solving for N2, so I'm going to circle that. And I just do that because it's easier for me to cancel things and rearrange it when I have whatever I'm looking for on top. If it doesn't bother you, you don't have to do it. It's just when I flip it real good, I say, it helps me. So that gives me, so I'm going to multiply both sides by V2 to get rid of that. So V2 goes there. So I've got V2 N1 over V1 equals N2. All right. So sorry, V2 times N1 over V1. I wrote it, I didn't say it, equals N2. All right. So I look, I've got liters, I've got moles. I'm looking for moles. So all I have to do is plug this in now. So V2, which was 2.55 liters, and make sure you look really closely as to which one is which. And that's why you really need to do it over here in your inventory, because sometimes you'll have to be changing things. And so if you already have it written down, it makes it a lot easier. So that's V1. All right, and so I'm going to get 0.105 moles. Now, some of you would stop there and you get half credit for this because I asked you, and I tried to say this up front, how many moles are exhaled during exhalation. So you got 0.105 moles left, and you had 0.254 initially. So what he exhaled was the difference between those. So 0.254 minus 0.105 is going to be 0.149 moles. Okay? And so that's just kind of like a little extra thing. Don't assume that every problem is going to be like that. Sometimes they'll just say, you know, after exhalation, how many moles did he have? And then you would just do it directly. But since they just said how many does he exhale, then you've got to do that difference. So you think about, when you're, instead of blindly working a problem, you definitely need to think about, what is it asking me for, and write that down. Okay, and that's why I put myself a little note here to remind myself. And of course I give you a practice for that. All right, so we have now talked about the relationships between pressure, volume, moles, and temperature. And so I can combine all of those three laws together and come up with what we call the combined gas law. And the combined gas law allows us to work any of those problems when we're changing these parameters. Even if we changed more than one thing, we could still put this in there. Okay, so we can use this. And the beauty of using the combined gas law and remembering it, this is how I remember it, that pigs vomit over nasty troughs. Now that's just disgusting enough that you might remember it. Like, I've remembered it for like 40 years or something. My first chemistry teacher that I ever had did this. Pigs vomit over nasty troughs. And I never forgot the combined gas law, because it's just gross. Okay, so P1V1 over N1T1 equals P2V2 over N2T2. Notice here, I got this from another book, and so they used initial and final instead of 1 and 2, but it really doesn't matter. Okay, as long as you have the correct things together. So when you have the combined gas law, you can work any of those problems with. But if it was holding volume and temperature constant, then you would just not use those, because they'd be the same on both sides. And so that's P1 over N1 equals P2 over N2, and we didn't even talk about that one. Okay, so you can use this to do whatever, and then just get rid of any of the things that are constant. So if they're constant, they cancel, which means you don't have to put them in. You can, but the numbers will cancel if you put them in there. So if it says at 25 degrees we did this, well, that means it was 25 degrees the whole time. So temperature is the same on both sides. All right, so that was the combined gas law, where we combine all of the gas laws into one combination. The combined gas law we use when we change something. So you will have two sets of data. You will have a first condition, and then you will change one or several of these, and you will get a new condition. And so when you do that, you're going to use the combined gas law to work one of those problems. Okay. Another way to combine these is into what we call the ideal gas law. And the ideal gas law is PV equals nRT. All right. P is pressure, and this one is very specific. Okay, units are specific. They have to be in these units in order for you to use this. And I'll show you why. Volume has to be in liters. Temperature, of course, has to be in Kelvin. N has to be in mole. And the reason is because R is a constant, and the constant is 0.0821 liter times atmosphere over mole times Kelvin. So since your constant has those units, then what you put in your formula also has to be in those units. So in these problems, it's just going to describe a situation. It's describing one situation. It's not changing the volume or the temperature or the pressure or anything. It's describing one situation, okay? And so if you're not changing anything, then you know you're going to use the ideal gas law. And you can use one of those two, combined or ideal, to work any of these problems. And this is just showing you how they came up with it, okay? And they did use the 3 simple laws in order to come up with that. So calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atmospheres and a temperature of 315 Kelvin. Now, those of you who want to be defiant and not take inventory, this is where you're going to get in trouble. Because if I take inventory and I see what I have, that's going to tell me whether I have enough stuff, like more than one V or more than one T, to use the combined gas law, or if I'm going to use the ideal because I only have one of everything. Okay, so I have moles are 0.845. I have a pressure of 1.37 atmospheres, and I have a temperature of 315 Kelvin. Now notice on this first one, I'm taking it easy on you, and I've already got stuff in the correct units. I just described one situation, okay? The other thing I know, which I didn't say on here, is that I know R is 0.0821 liter atmosphere over mole K. So my ideal gas law is PV equals nRT. So I'm solving. The only one I'm missing is volume, right? So what is the volume? So I'm going to get volume by itself over here by P, right? And I'm going to come up with V equals nRT over P. And so I've got moles, I've got atmospheres, I've got Kelvin, and then I've got my constant. So I know everything is going to be lovely. So I've got 0.845 moles. I've got R, 0.0821 liter atmosphere mole K. And I've got temperature, which is 315 K. Hopefully you can write it neater than I did. And so then, the pressure was 1.37 atmospheres. So V is going to be 15.9 liters because I have moles, moles, atmospheres, atmospheres, K and K. So I'm only left with liters. So see how the constant does that? And so if you don't end up, when you cancel things out, with the right unit, you need to go back and look because you probably did something wrong in the formula. You did this wrong usually. Okay? So ideal gas law is pretty simple. You just need to know 3 of the parameters, and then you can figure out the 4th one. So there you are with one to work with. All right. So, and I don't know why they have to put all these words in here. So they want to know how many moles. So I know N is what I'm looking for this time. All right. And so I'll already give you a hint too. Like as we progress through this, if it starts asking for grams, you're going to be solving for moles first using this formula typically, and then you convert it to grams if you know what the gas is by using its formula weight. But that's something that we'll do later. All right. So calculate the number of moles in a 3.24 liter. That sounds like a volume. Basketball inflated to a total pressure of 24.3 psi. Okay, and then it's telling me total pressure is not the same as the pressure read on the type of pressure gauge used for checking it. That pressure is called the gauge pressure, which is the difference between total pressure and atmospheric pressure. Atmospheric pressure is 14.7, so the gauge pressure would be 9.6. However, for calculations involving the ideal gas law, you must use the total pressure. Okay, so really didn't need to know all that stuff, but anyway. All right, so pressure after all of that is 24.3 psi. All right, so I know N, V, and P. R is my friend, 0.0821. And I do this every time. I know y'all are thinking, I ain't going to write that. I do it every time because that reminds me that I have to have the same units. And so I have 24.3 psi, and I need that to be in atmospheres. Okay, so I can either go ahead and look that up, but on a test you're probably going to need to change it. All right, so I know that there are 14.7 let me get where my numbers are. 14.7 psi. So I'm going to go ahead and do that first in 1 atmosphere. And that allows me to convert that to atmospheres. So that's 1.65 atmospheres. All right. So I now have liters, atmospheres, and I have the, oh, and it told me the temperature, didn't it? Temperature. That's the other thing I have to have, right? And it was at 25 degrees C. And so I know because I'm using my R that I have to get that to Kelvin. So that's 298 Kelvin. So I've now got everything in the same units as my R. So I've got liters, atmospheres, temperature in Kelvin, and then that. So now I'm ready to plug it in, and I'm looking for E. So PV equals nRT, and I'm solving for N. So I'm going to divide both sides by RT. So N equals PV over RT. I don't know if y'all can hear my dogs howling, but I apologize. They can be real idiots sometimes. All right, so now all I have to do is plug in 1.65 atmospheres times the volume, which was 3.24 liters, divided by R, 0.0821 liter atmosphere over mole K. And then times temperature at 298. All right, and so K's will go away, and atmospheres will go away, and liters will go away. And if you recall, when you divide by something that you're already dividing by, that's the same thing as moving it up. So we will end up in moles. And you know that you can go on to mastering and do the tutorials. They have math concepts by topic. So that's always a super good idea to do that if you're rusty on anything. So 0.219. I also have a practice sheet on there on rearranging formulas. So, all right, so we get 0.219 moles. And remember, if I know, if this was just like oxygen instead of like air, which is a mixture of a bunch of stuff, if I knew this was oxygen, then I could go ahead and figure out how many grams I had in there, because if I know the gas, I can figure out the formula weight. So, and that's usually what you're more interested in the real world, is how many grams or kilograms, milligrams. And you have a couple to practice. Notice I give you quite a few to practice on this because you're going to see quite a few of these types of problems on your exam. All right, standard conditions. So if we're going to make a table of properties of things, we have to have some things standardized. And so for gases, it's 0 degrees Celsius or 273 Kelvin. It's 1 mole of substance, 1 atmosphere of pressure, and the standard volume is 22.4 liters. And those are very important. This is another thing that we got from Avogadro, and this is called the molar volume. So if you have 1 mole of gas at 0 degrees C and 1 atmosphere of pressure, and using the constant, and I know they use 0.8206 this time, but your number is going to be basically the same to 3 sig figs. You're going to get 22.4 liters. All right, and 22.4 liters is what we call the molar volume of a gas. And the cool thing about gases, and how another way they're different from liquids and solids and things like that, is that liquids have different volumes, okay? So depending on how much you have, they have volumes. But since gases are compressible and they move differently, the molar volume is what you have 6.022 times 10 to the 23rd molecules of gas. But what's interesting is if you had a mole of helium, you would have a different amount in grams than you would, right? CH4, which would be 16 grams, right? Or no, 12, yeah, 16 grams. And I don't know what xenon is. So 1 mole of helium is 4 grams. 1 mole of methane is 16 grams. And that's the formula weight, okay? And xenon is whatever it is. I'm not looking it up. So, but the molar volume is the same for each one at standard conditions. So 22.4 liters is 1 mole of helium. 22.4 liters is 1 mole of xenon, and 22.4 liters is 1 mole of methane. So they all have the same molar volume as long as they are at 0 degrees C, 1 atmosphere of pressure, and 1 mole of gas, right? So they always have the same one. So even though they have different molar masses, they have the same molar volume. So that 22.4 liters is the molar volume, and that's just something that you need to keep in mind. Excuse me. I know that I've seen if students get in trouble in a problem, sometimes if they think about the molar volume, it'll get them out of it. This is only true at what we just define as STP. That stands for standard temperature and pressure, right? So that's 0 degrees C and 1 atmosphere. So standard temperature and pressure is the volume that. That's the only time you can use it. If the temperature is 25 degrees, you can't do it, all right, because it will change if you change the temperature, all right? So as part of this, all right, we look at the density of a gas. And the density of the gas, just like density of a liquid, is its mass divided by its volume. So mass compared to volume. But in gases, we generally use grams per liter instead of grams per milliliter, okay? So liquids are grams per milliliter. But gases take up so much more space that we do it grams per liter for gases, okay? So the mass of 1 mole of gas or whatever is the molar mass, and the volume of 1 mole at STP, 0 degrees C, 1 atmosphere of pressure, is 22.4 liters. And so if you have the molar mass divided by the molar volume, that's going to be the density of the molar density of the gas that you would typically see. Okay, So molar mass over molar volume is going to give you the density in grams per liter. So if we look at our helium and nitrogen, okay, helium, that's 4 grams per mole, and or is it 2? Anyway, nitrogen is 14. Wonder how come I know that one, and I can't remember helium right now. The inert gases, the noble gases have left me for a while. Okay, so anyway, 2 or 4, whatever that is. Oh, it's 4. Okay, so you got 4 grams per mole divided by 22.4 liters per mole. So the density of that gas at STP is 0.179. Why at STP? Because if I change the temperature, I'm going to change this number. Okay? All right. And the density of nitrogen at STP is 1.25 because it's 14 grams times 2, right? Because it is a diatomic gas. Don't forget which ones those are because it's super important in the gas chapter. Hydrogen, nitrogen, oxygen, and fluorine, chlorine, iodine. Okay, bromine. Okay, all right. So just remember when you're doing your molecular weights that you have to take that into consideration. So one way as chemists, we can determine the molar mass of an unknown and figure out what it is in, like, for instance, to heat a weighed sample until it becomes a gas. Once it becomes a gas, we measure the temperature, the pressure, and the volume, and then we use the ideal gas law to figure out what the molar mass is. So that molar mass is proportional to the density. All right, and so this I give to my mathy people because they like to see how things are derived sometimes. But what we're going to use is this density formula right here, that the density of the gas is equal to the pressure times the molar mass in grams per mole divided by R and the temperature in Kelvin. So pressure times molar mass times R times temperature. So this is your density formula. So if I ask you what the density of a gas is and I give you some stuff, you can figure that out. Also, if I tell you what the density is and I tell you the pressure and the temperature, you can figure out what the molar mass is. Okay? So density in grams per liter is P times M, molar mass, divided by RT. So all of that for that formula. All right, so calculate the density of nitrogen gas at 125 degrees C and a pressure of 755 millimeters mercury. All right, nitrogen is a diatomic, right? N2. So I need to remember that. If it was hydrogen, if it was oxygen, those would also be diatomic. That's important because I know the formula weight of that is 14 times 2, which is 28 grams per mole. And if I used 14, I'd be off by a factor of 2. So inventory. The formula weight of nitrogen is 28 grams per mole. The temperature is 125 degrees C. The pressure is 755 millimeters of mercury. All right, so density. So my formula is there. Density equals pressure, I got a pressure, times the formula weight or molecular weight. They're using M, so I'll change that to an M. Molecular weight, formula weight, same thing, is 28 grams per mole. and it gives me a T, and I also need R. Now remember what that is, 0.0821 liter atmosphere over mole K. Constants, the reason constants are different in different books is because they do them to different numbers of sig figs. 0821 is what I always learned it as, and so that's what I usually write it down. If you do 08206, it's not going to make that much difference, that fourth decimal place. So, you know, it's up to you. This is just rounded to 3 sig figs. Okay, so I know what my formula is. I'm going to be using R, and I wrote the units to R down to remind me that I have to change these units. Okay, so I've got grams per mole up here, that works. I've got 125 degrees C. I've got to change that to Kelvin. And so that is going to be 398 Kelvin. I have a pressure of 755 millimeters of mercury. And if I look back on my chart, or I have it memorized already, there are 760 millimeters of mercury in 1 atmosphere. And so that's 0.993 atmospheres. All right. Is that everything? I think. Okay, so I'm going to write this formula down. So D is equal to P. Notice that M is kind of, it's written different from like molarity, okay, because that's molar mass they're talking about, over RT. So D is equal to the pressure in atmosphere, 0.993 atmospheres times 28 grams per mole divided by 0.0821 liter per mole K times temperature of 398 K. And so when I get rid of all this stuff, so K and atmospheres and moles and moles, and I'm left with grams and liters, which is what I want. And so when I do those calculations, if you get what I got 0.851, and if you get 52, that's okay, grams per liter. Remember, these, when you're off to that third decimal place, I don't get worried about it. As long as you show me your work, I know you knew how to work it. When you get to your job, or when you get to higher levels of this course or other scientific courses, they will tell you what degree of accuracy and precision they want. Okay, so that's calculating the density of the gas. And again, you have multiples, and if you'll practice these pretty soon after we go over them, then they'll stick with you a little bit better. Okay, so we saw how you could get density from, if you know what the gas is. Mostly what the application for this is if you don't know what the gas is and you're trying to figure out what the gas is. Okay, so in this is a perfect problem for this. So we use these a lot of times. We just have a mass spectrometer now, and that we can do it, but you can do it without one that costs, you know, hundreds of thousands of dollars. And it's actually just as accurate, just saying. But you have a sample of gas, and it has a mass. Okay, so it has a mass of 0.311 grams. I know that because I measured that in the lab. I measured 0.311 grams. I can't measure moles, right? I only can do grams. And it has a volume of 0.225. So I took 0.311 grams of gas, and at that amount, it had a volume of 0.225 liters, and I had to have it at a temperature of 55 degrees C in order to get it to become a gas. And the pressure that I had it under was 886 millimeters of mercury. All right, and it wants to know what its molar mass is. All right, so when I'm looking for molar mass, okay, I'm going to have to know moles first. All right, so if I'm looking for moles, I'm going to be using PV equals nRT. Okay, because it's not something changing, so I can't use that first, the combined gas law. I can only use the ideal gas law, which is PV equals nRT, because I'm looking for N moles. So PV, wait, I'm going to do it over here. PV equals nRT, right? I'm going to be looking for moles. Why? Because what is molar mass? Molar mass is grams over moles. And I already know what the grams are. So if I can find out what the moles are, then I can just do this at the end and find out what the molar mass is. So, but I am going to have my parameters in, since I'm using PV equals nRT. All right, it's not at STP, so I can't use 22.4 or anything like that. It has to be at 0 degrees and 1 atmosphere of pressure if I do that, so that's not going to work. So I'm going to have to convert this to Kelvin because I'm using R. If I look at the R, then I know that. That's going to be 328 Kelvin. And my pressure is, I know that in 1 atmosphere, 160 millimeters of mercury. So that's 1.17 atmospheres. That's pretty strong. Okay. So now I've got Kelvin, liters, atmospheres, R, and the only thing I don't have is N. So anytime it gives you a mass or it asks for a mass, you're going to do it in moles first. Okay. All right. So PV equals nRT. I'm solving for N. So RT, so N equals PV over RT. After you've done these enough time, you're going to remember some rearrangements, okay? All right, so N equals PV over RT. So since I have everything in the correct units, N equals 1.17. And I'm not going to write the units. I've already showed you that they'll cancel. 0821. Make sure you put that O before that number too, because if you don't, you're off a magnitude of 10. And then temperature. All right, and that is going to give me 0.0098 moles. And you're going to see little numbers for these, so don't get too excited when you see something like that, because moles of gas are small. Okay, so all right, so N equals 0.90098. So I'm looking for M, okay, and M is going to be grams over moles. So I go back to my grams, which I had at the beginning, 0.311 grams divided by the number of moles, 0.0098 moles. And that's going to tell me that the molar mass is 44.0 grams per mole. And if I worked in gases a lot, I would recognize that because I'd have a list of molar masses of gases, and I could actually identify this as CO2, which is 32 plus 12 is 44. Now, I don't expect you to do that. Don't get excited. But, after you've done it for a while and oh, 44, that's CO2, or 32, that's oxygen, or whatever. So you could identify the gas. Okay? So that's how you do the molar mass of a gas by using the ideal gas law. Here's your practice, and we are done for the day. I know you're sad. So the first half of this chapter was Boyle's, Charles, Avogadro's law, the combined gas law, where you just basically combine all of those, and then the ideal gas law, which is where you have a condition that you're describing, the combined gas law, where you have a condition that you are changing. So you have two different situations. So you just got to keep that in mind so that you know when to use what. You also learned about STP, standard temperature and pressure. Standard temperature and pressure is specifically 0 degrees Celsius or 273 Kelvin and 1 atmosphere pressure. If they're not under those, they are not under standard conditions. All of the things that we're talking about are typically standard conditions, and when we're talking about the ideal gas law. All right, you do have a gas lab, which you're going to see some of these different gas laws in action. So make sure you do those if you haven't already done them. All right, that's all I have for today.